So my name is John Oskin, Senior Vice President with SmartSites. Today's topic is the evolution of data collection in manufacturing and how that has evolved into what everybody knows today as Industry 4.0 and how it is being used to drive digital transformations. So we're going to start by talking about the evolution of data collection, including the evolution of alarm data, and then some specific needs that we see in terms of high volume industries, as well as application needs for data around CMMS, SBC, OEE, SCADA, et cetera. And then really kind of showing you how we've gone from really manual data collection to what is known today as digital transformation. So that'll be our agenda for today. So let's start by talking about the evolution of data collection. So if you think about the pre-1970s and what was in place, really you have a manual paper-based systems. Operators recorded data on clipboards, production counts, downtime, quality checks, et cetera. From a data accuracy standpoint, it was low, it was prone to human error, and really very difficult to get insights when you have a paper-based system. The focus back then was really based on just compliance and record keeping. Then in the 1970s through the 1990s is really when PLCs took hold and really started this journey around automatic data collection. So data was siloed though back then, even though you could get some data from PLCs. Back in the 70s and 80s, most PLCs weren't even capable of providing data. They're really focused on machine control. Then as you moved into the 1990s, this is really when manufacturing execution systems took hold. And with the advent of MES systems, what you found is there was this capability now of getting some automatic data collection coupled in with integration with ERP systems. Data collection then expanded into OE applications, and then also traceability and batch record recording. The data collection back then was really kind of shift-based, but not, from a machine level standpoint, it really kind of focused on line level kind of data collection. And then the focus for that kind of data was really around just efficiency, quality management, and regulatory compliance in some industries. Then you kind of move into the 2010s until kind of today, if you will. And this is really the advent of IIoT, Industrial Internet of Things. This is where companies started to deploy sensors, IoT technologies, and edge computing. And with those kinds of technologies, you really enabled a whole new level of real-time data capture. Cloud platforms emerged where you weren't reliant on on-premise data collection systems. And with that, you have today large-scale data storage, analytics, remote access. Most of what everybody knows today is kind of modern, contemporary data collection. The focus shifted from efficiency and quality management into things like predictive maintenance, advanced analytics, and then really digital twins, which is kind of one of the newest technologies to emerge. So now when you kind of look at today and kind of moving into the next 10 to 15 years, if you will, we see a convergence of AI, machine learning, autonomous systems, and all this provides real-time data that is contextualized into actionable intelligence. So if you think about collaboration now with data, you're now able to bring together suppliers with OEMs, with factory floor operators, and with that, standardizing the data streams for analysis. So the focus now has moved into predictive and prescriptive insights. So not just reporting on data and focusing on historical data mining, if you will. It's really kind of moving into this new arena of predictive analytics and what we describe as exception reporting. So rather than reporting on all data, it's really reporting on when anomalies occur and what actions need to be taken when those anomalies are observed. So the evolution that we've seen in data collection is this journey from kind of manual data collection, which was delayed and siloed data, into now what you have is real-time data, integrated data, intelligent data that are now powering smart factories. If we look at the evolution of alarm data in manufacturing, it has a similar journey. So pre-1980s, what you had was really a manual alarm process. Toyota pioneered the concept of Andon. Andon was a pull cord concept where if there was an issue, there was a pull cord over the line, an operator would pull that cord, the line would stop, operators would huddle up, they'd discuss the problem that they were having, and then that would get resolved, and then they would start the line back up. So there really was no permanent record of alarms at that time, limited local awareness, but focus on problem solving. That moved from manual alarming with, again, this pull cord concept into the 1980s and 90s, where we got into basic digital alarm applications. And with that, what you saw was the emergence where SCADA data and PLC data can now log alarm conditions. And those alarms were generated, but some cases they were overwhelming. So you might have hundreds and thousands of alarms, some of them nuisance alarms. And so it was kind of difficult to parse through all that information. Data was still local to the control rooms, so very much kind of a siloed approach to who had access to alarm data. Then when you think about the 2000s, you got into centralized alarm management. So this is the emergence of historian databases. So now you can have archived alarms, and then alarm rationalization. So rather than being overwhelmed by alarms, you had a way of really discerning which ones are the most important ones. And then with that came reporting and compliance. As we moved into the 2010s to really kind of present day, if you will, alarm data is now being integrated with MES systems, CMMS systems, and even OE kind of systems. You're seeing mobile and remote notification in the process. And then, heavier analytics associated with the alarm data. And then similarly, with the alarm data kind of moving into, the next 5 to 10 years now, we're seeing this need for predictive and prescriptive alarm data. So again, giving people the alarms they need, arming them with predictive information so that they can kind of take actions. Next topic I want to talk about is just the data needs for high volume industries, because they are kind of unique. So high volume industries include food and beverage, consumer packaged goods, automotive, any kind of fast moving consumer goods sector. And what you find is that the needs in those industries require scale and speed. So it's thousands, in some cases millions of units produced daily, and any small efficiencies can result in major cost impacts. Minor stops in this industry is a huge problem. So this downtime sensitivity to minor stops necessitates a need for real-time data collection. So here's a couple statistics for you. So on a food and beverage packaging line, an average line will stop 20,000 times a year. Just think about that for a minute. There's no way you can do that manually, okay? It requires automatic data collection. It requires automatic capture of reasons for why these lines are stopping. So that necessitates the need for this real-time data collection. Then you have regulatory and traceability needs. So whether it's for food safety or for pharma compliance, the traceability and regulatory needs have also escalated. So in the pharma sector, if you're doing automatic data collection and that data collection involves modifying the PLC programs to enable that kind of data collection, that can be very expensive. In the pharma sector, to revalidate a production line can take anywhere from $500,000 to $1 million for revalidation. So data collection can be very expensive in that industry. And then the last really is around complexity. So if you think about these high volume industries, They're processing multiple SKUs, frequent changeovers, and with that, it necessitates the need for better context. So with multiple SKUs being run, gone are the days when a production line would run an entire day, in some cases an entire week. Now you're seeing production lines change on an hourly basis, or every other hour. And so with the frequent changeovers that are occurring, what you find is that in itself can create disruptions on a production line, but then also provides a need for understanding, which product SKUs necessitate more complex changeover requirements. And even from an understanding of an OE perspective, in terms of which SKUs are more efficient SKUs or less efficient SKUs, based on things like, the kind of, changeover that's required for that SKU, or nuances associated with that SKU. Maybe it's a plastic bottle versus a glass bottle that behaves very differently. So really having the context associated with data collection is what really enables further analysis. We talk about the data needs for some of the modern factory floor business systems, such as computerized maintenance management systems, statistical process control applications, SCADA or OE applications. There's also a unique need for those kinds of applications. So starting with CMMS, pre-2000, if you will, you had maintenance data that was entered manually. Somebody had a work order, they'd fill out a work order. Again, think paper-based systems. And CMMS enabled that to be done automatically. So reactive maintenance dominated. So it focused on, what would occur that would require a maintenance person to come to the floor to fix a machine. It was less focused on proactive maintenance. And so what CMMS systems enabled was the ability to have proactive maintenance work orders, so that something might be done on a weekly or a quarterly basis to prevent a catastrophic issue from occurring. Pre-2000, the data lagged. It wasn't necessarily real time, and it reduced its value as a result for decision-making purposes. Now, if you think about today's era here, you have automatic data capture from sensors and IoT devices that can feed directly into CMMS applications. The classic case for this is what is known as meter readings. So if you have a CMMS application, rather than saying that every 3 weeks we're going to do some type of a PM activity on a machine with an IoT sensor or signals that might indicate things such as product flow or even uptime information on a machine, you can now say that after 500 runtime hours or after 10,000 parts, I'm going to trigger a work order. So this is some of the more modern techniques for infusing data collection into CMMS applications. And then with that, you have predictive maintenance that comes out of that. So once you start getting all this data in and tied it in with the CMMS application, you can now see what where the needs go next. If you look at the data needs for statistical process control and SCADA applications, SPC heavily relied on manual sampling and charting. As a matter of fact, there are some kind of SPC traditionalists that used to think that it was important to have an operator, writing down those samples and actually charting them on a piece of paper, just so that they understood the SPC process. That thinking has evolved over the past 20 years, and really what you find now is that it has moved from manual sampling into automatic sampling. So pulling the data from different types of gauges, in some cases, machine control systems, et cetera. So you're unburdening the operator from having to do that manual sampling process. You're still using SPC principles for analyzing the data. So you're looking for out of control conditions. And with those out of control conditions that can be automatically identified, now you can take action on those. From a SCADA perspective, SCADA today allows you to kind of feed data streams into enterprise data lakes. So with that, you get a whole new level of analytics that go along with SCADA data. For OEE systems, OEE was typically calculated manually. As a matter of fact, OEE today can even be calculated on a cocktail napkin. It's a pretty simple formula. However, for OEE, it's not about the number, it's about the losses against the number. And for that, you need automatic data collection. Back in the day, data was, backward looking, it was used for reporting, and it certainly wasn't real time. So today you have real-time OEE dashboards, automatic downtime categorization. Operators are too busy now to identify losses, certainly on the high volume operations. So being able to get reasons for downtime from the PLCs is an important concept. And then with that, you can now standardize OEE metrics, certainly across lines and across plants, and we found actually across industries. So we benchmark OEE, and some of the benchmark statistics that we report, the overall industry average for OEE is about 62%. Best in class is actually about 82.5. A lot of people like to tout best in class is 85% for OEE. We report 82.5 because we use a top quartile concept when we do this kind of reporting. So that means that from a top quartile perspective, 25% of a sampling group can achieve that level at 82.5. So it's attainable. Okay, there are companies out there, there are operations out there that could be running 90-95% OEE, but they tend to be kind of selective. So again, industry average tends to be about 62%. If you actually go into the pharmaceutical sector, it's actually about half of that, about 30%. So huge opportunity for improvement. So with that, starting with this journey from manual data collection from years past to today, which involves modern real-time data collection, and then moving into digital twins, that's really where data collection is going. So why do digital twins matter in data collection? Well, first, it's just to provide a virtual replica of a production system. So historically, this was done through simulation. So simulation packages, in years past, you would usually provide a throughput rate, how many units per minute or per hour are you producing at a machine center? And then if it was available, you might provide a statistic like what is the mean time between failure for that machine or operation? What is the mean time to repair? And with those three statistics, fitting that into a simulation application, you can actually simulate out of factory. What you have today with digital twins is the ability to kind of do this on a real-time basis. So being able to take very rich historical data to create models that then can kind of simulate real-time scenarios for purposes such as line balancing, developing maintenance schedules, or even recipe changes. Along with that, you have the capability of doing predictive analytics. So with a lot of really rich information, feeding that into AI models, you can now use machine learning with that live data to actually forecast and project equipment failures, scrap rates, and even throughput bottlenecks. Closed loop feedback. So with a digital twin concept, now you're able to then feed back information from the machines and operators in real time. And then finally, scalability. So if you're a business that has multiple factories, being able to kind of use a digital twin concept that can be applied from one factory to the next becomes particularly important in those high volume industries. That helps with benchmarking and then enriching the data twin models. So Smart Sites has a set of tools and technologies to support things like advanced data collection, issue management, and reporting. We do that with a suite of products, starting with a product called Able, that is the advanced data collection engine that can work with a variety of systems. Peer, which is for issue management and collaboration. And then SmartSight's hallmark product, which is Win911 for advanced alarm notification. So starting with Able. So what is Able? Able is an advanced data collection engine, and it's an accelerator for digital transformation initiatives. What it does is it models machine centers, and it couples it up with line flow. That's an important concept. So it's not just getting data from an individual machine, it's taking the related and adjacent machines and providing insight and information about how one machine center affects the next machine center. It supports a corporate PLC standardization strategy, and it simplifies data acquisition and control architecture. So with the SmartSites Able technology, we do not require PLC programming. That's a huge difference in the market, okay? So what it does is it takes PLCs back to their roots and allows them to focus on machine control rather than data acquisition. And then with the Able logic engine, that could be used then to feed other business systems. So it has an enterprise configuration component to it, and companies that have implemented the Able technology see typically a 5x improvement in data fidelity and a 70% reduction in integration cost. So pretty impactful. Peer is the SmartSites issue management accelerator. Peer couples nicely in with the Win911 application. So what it does is it captures issues and it sets priorities. It triggers alerts for responsive action, and then it creates follow-up with accountability. And with that, we are connecting issues with systems, and we're building a knowledge base of corrective actions. So with Peer, issues can be addressed one of three ways. It can start with the Win911 alarm that might trigger a Peer ticket. It might come from a PLC system where we're grabbing PLC data. Maybe it's a downtime trigger. For example, machine down more than 10 minutes might drive a Peer ticket to maintenance to be summoned to the line. Or it could be manually initiated. It could be initiated by an operator as a call for help mechanism. Think about the Toyota concept that I mentioned earlier in our discussion, where an operator would pull a cord and bring attention to the line problem. So today you have that mechanism, that operator call for help embedded in the Peer application. And then with Win911 and Excel Reporter, you have really advanced alarm management and reporting. So with key capabilities such as mobile alerts and audit reports, but the key thing is having live alarm metrics and giving you this holistic process summary of your alarm data. So with that, let's take a look at what advanced data collection looks like with some of the SmartSites products. So this is the Able configuration utility. It's a drag and drop type of interface. And here we've got a factory with a processing area, a press area, a work cell, and in this case, a packaging line. And so the process starts with modeling out a production line. So in this case, it's a drag and drop process. So I can say, okay, I have this molder and this molder, maybe feeding into a press operation. Okay, so you sort of drag those into view, and then I start connecting up. And when I connect up, it asks me, do you want to add root cause to the existing condition? I'm going to say yes. That's an important concept, because now what we've done is we have bound these two assets. Press 1 knows that molder 7 comes before it. Okay, and then if I keep the process going here and I connect up another machine, press 2 knows that press 1 comes before it. So you can start building out these complex line flows. That's an important concept when we start doing the root cause analysis. Then if you kind of go into a machine center, there's details that you put in there. So, what PLC is it in? What type of an asset is. We have, 4 types of assets. So there's a line asset for a production line. A cell asset is a unit operation. Think of a machine center. So like in a food and beverage plant, filler, carton, or case packer, each one of those is a cell asset to us. Secondary assets tend to be feeding operations. So if I have a case packer, I probably have a case erector going, feeding into that case packer. So that's considered a secondary operation. And then I have virtual assets, and virtual assets are where we create groups. So if I have a filler that then feeds into 3 labelers and then comes back together into a case packer, those 3 labelers you may want to look at individually, but you also want to look at them collectively. So you can create a virtual group for that labeler group. So that data can then be analyzed, and then obviously looking at them individually. So items are where we have detailed information around the state logic associated with the machine. So with Able, we identify state status as either running, starved, blocked, or vaulted. So this is signal information that drives that logic level. And then you have conditions, and the conditions are the meat of all this. So you have a running condition, you have starved conditions, block conditions, and then typically many faulted conditions. Once all of this gets configured, it goes into runtime mode. So here's what it looks like in a runtime mode. So in runtime mode now, what we're doing is we are having a real-time view of the factory. So coming back to the architecture that I showed you for the plant, this processing area, press area, and then the cells in the packaging line, if you will. If you have a very large factory, this can get built out as large as it needs to go. You can also break a factory up. So here we've got an overall factory view, but let's just say I am only interested in my assembly area. So if I develop a view for that, it's just going to focus on the work cell and that assembly line operation. Going back to that factory view, though, once we start getting data collection going, I'll show you what it looks like here. So if I actually click on one of these machines here, it's actually going to give you some simple analytics. So, things like percentage of time that machine is running, and then percentage of time of why it's down, waiting on material, chute blocked, low fill, so on and so forth. If Able is being fed into an MES system, it can be architected into multiple levels. So you can have up to 5 levels for details. So it doesn't have to be just this top level set of reasons. I might have a secondary or a tertiary set of reasons. But this is what the raw data looks like. So when we talk about advanced data collection, this is what we're talking about. We're talking about detailed data collection, minute by minute, accounting for every minute of the day. So here you're seeing we're toggling between running and down, running and down. And then if I'm down, it's giving you details around what happened here. So in this case, it was a chute blocked. So this is kind of where some of the root cause information kind of comes into play. This is the information that typically will get fed into an MES system. So it's this level of detail that gets passed over and absorbed by the MES system. And then the MES system has additional context. It has context such as SKU information, production order data that comes from the ERP system, so on and so forth. So when you start getting this really rich data, this is where it gets interesting. So I'm going to focus on that assembly area, and specifically this packaging line, if you will, that we have. So we've got, in this case, we have generically, we've identified it as just operation 10 feeding into operation 20, and then operation 30, and then operation 40. So these are the unit ops. This oval asset represents the production line. And what its job is to basically roll up what it's seeing at the unit op level into a root cause analysis construct. The way to visualize that a little bit better is through the DNA view. The DNA view is essentially a Gantt chart concept, but it looks like a DNA chart. And so what you see here is I have the line at the bottom, I have my unit operations above it. So op 10, op 20, 30, 40, right? And so with that, if I just zoom in, you can start to see what happens is that, first of all, you see when you get these really minor interruptions that are occurring. Again, remember, in the high volume industries, production line will stop 20,000 times a year. That's this stuff, 1 minute, 2 minute, 3 minute kind of events. And then you have bigger events, okay? So visually you're seeing, both the minor stops, but then also the major stops. And then regardless if a piece of equipment goes down and it starts cascading through the line, you see that as well. So here you can see this operation 40 kind of, the leading edge of that started a downtime sequence that then took out the other operations. A better way to understand that is through the digital twin replay functionality that is part of Able. So if I click on the replay button, this is kind of where digital twin now comes into play. So here you can see I've got my production line here. I'm going to go ahead and make that bigger so that you can see it on screen a little bit better. I'll kind of, it creates this split screen view. So I'm going to kind of bring the DNA chart now into focus. And if I click on the play button, it's literally going to start replaying minute by minute my historical data. I could go back in time as much as 30 days. Typically for a digital replay, you're only going to replay something that is either today or maybe a day or two old. But I can fast forward it. So now I'm starting to speed through the data a little bit. I can pause it. And then more importantly, what I can do is I can slow walk it. So if I can slow walk it, I can get to a downtime sequence here. So let's start with this sequence here where operation 40 went down. You can see how operation 30 then backs up, operation 20, and then operation 10. And at that point, the line asset picked up on that. It does what's called first fault capture. So it knows that operation 40 initiated this, and then everything else was a slave to operation 40. So, and then with that, it's able to discern that the line went down due to operation 40. And then it also interrogates the PLC. It knows the faults in the PLC to know that there was a discharge issue there. So we're pulling that information as well. So very powerful concept for being able to kind of replay data to understand a downtime sequence better. So in an MES deployment, this is a very important concept because in an MES application, it takes an enormous amount of time to validate data collection. And 90% of the data validation can be done through this interface remotely. So you don't need to send an engineer on site. If you're a systems integrator, it's going to be done remotely. And then maybe you have someone on site for kind of that last mile data validation. But rather than spending 6 weeks on site doing data validation, you could probably spend a week on site and doing the rest of it kind of remotely, if you will. The nice thing is that when you see anomalies, okay, so something doesn't quite look right, or it's just something you want to share with the team, I can share this sequence. So if I create an email link here, basically it's going to create an email here and with a hyperlink to the date and time in question. And then you can add your own comments here around, hey, I noticed that we had this unusual downtime sequence. Maybe there was a crash on third shift that that caused this sequence to occur, if you will. So that is a little bit on these DNA views. The other thing when it comes to digital twinning, kind of going back to the simulation discussion, are some of these other kind of important KPIs. So we can going back to that layout view. If I go back to the overall factory view again that we started with, we can create heat maps for some of the key KPIs used for simulation. So starting with an availability heat map. So visually, it's the same view, but the data that we're showing is different. Previous view is just giving you a real-time view, what's running and what's down. This is a KPI view here. So this is showing you, in this case, machine availability. So you can see all these machines are in green, except for this one here, press 1, which is in red, okay? It's 75%. It has target thresholds that if I'm below 80, I'm in red. If I'm above 99, I'm in green. That's why it's in red. So this is, something to pay attention to. Mean time between failure. So if I apply that KPI onto the heat map here, now you can see I have many machines showing up in red. But then if I flip to MTTR, mean time to repair, everything's back in green. So all these data points can then be fed into a simulation application for further analysis, if you will. So that's a little bit about advanced data collection. Another concept I'll just quickly touch on is how we handle issue management. So if you'll notice in that layout view here, we had little phone icons. So this is kind of where the peer application comes into play. And I'm going to go to a different instance just to kind of show you that a little bit differently here. So in this case, I'm going to start with this layout view. So we have, and here we have a packaging line. So I've got an unscrambler feeding into an orienter, and then a filler, and then I've got a bank of labelers, and then a case packer, and then a palletizer. And there you can see the little phone icons. So there's a couple ways that a peer can be initiated. One is if the machines go down after X amount of time, I can automatically initiate a peer ticket. But I can also manually do it. So if I just click on this little phone icon here, it gives me a button here where I can click on, and what it's going to do is it's going to initiate a minor equipment repair for that machine, and it's going to send off an email to maintenance. And in this message center here, you can see that it's created this tile, which is what's called a peer ticket. And with the peer ticket, it's tracking an issue from inception through closure, okay? Another way that I can initiate a peer ticket is just manually from the operator. So you can have different types of tickets that can be initiated. It could be a maintenance related issue. It could be quality related. It could be safety. So in this case, let's just pick up a safety. Maybe there's a spill on the floor or something. So we want to create a safety ticket. So maybe that's something that's operator initiated as opposed to machine initiated. So by doing so, I get a form. I tell it what asset or area it's related to. If there's a workstation, I give it that detail. Who do I want to notify? So maybe in this case, it's maybe it's equipment repair team and maybe some kind of escalation team. So I can have multiple stakeholders, and I can have a different kind of status states for a ticket. So we're going to start by just initiating it. But then again, this is a safety kind of issue. So in this case, you might have a drop-down menu. All this is configurable. So in this case, we're going to just, it could be behavioral or environmental. These are just drop-down selections that get defined. So we're just going to say it's behavioral. And then you have an assessment here of what's the likelihood of injury. Maybe it's low because it's a spill on the floor. What's my observation category, if that's been defined. And then, here's my observation, which is, spill on the floor. If I want to attach a photo or a document, I would do that as well. And then I'm going to go ahead and submit it. And then that creates a peer ticket, if you will. So I've showed you two different ways that those tickets can be created. Once tickets start to get created, and I've got a couple here on screen that have already been created, I can always update the ticket. So I can go in and I can do a quick update like this one we just created here. I went from initiate to now I'm going to say acknowledge. So it's going to go yellow. But this one over here, this third one over, which has been open, if I click on the bottom half of the ticket, it's going to give me details I can fill in if I wanted to update more information. But the more important thing is I've got the peer issue timeline here, which is timestamping every step of the way. So when was the request made? When was it acknowledged? When was the repair complete, in this case? And then here, the ticket was actually reopened. So it was reopened for rework. So you're seeing all this get timestamped. Any fields that get updated get added into the peer timeline. And then ultimately, when it's ready to be closed, and I'll just go ahead and close this ticket out now. Now, once I've got a closed ticket, now I've got something I can report on. And that's the difference from just, issuing alarms, from taking alarms and having actions associated with those alarms. So with that now, I can go and I can start reporting on data here. So I'm going to take a look. I can do, year-to-date, month-to-date, week-to-date. I can pick my time frame, if you will. So now I can see how many tickets are getting closed, time between tickets, and then everything that has a drop-down selection is going to get paraded out. So, closed by line, if you will, by notification group, engineering versus quality versus management, status, by type, minor equipment issue versus a degraded performance issue, so on and so forth. So really rich analytics to go along with the data. This is what enables continuous improvement managers, maintenance professionals to then analyze, safety coordinators to analyze this kind of data to decide what further action needs to take place. So that's a little bit about peer and issue management associated with advanced data collection. So some key takeaways. So for Able, Able really represents a better data collection engine that can be used on its own or in conjunction with another system. So the key thing is that typical MES and OE data collection systems without the Able Logic engine can have some limitations. The biggest being that they typically require PLC programming. And with Able, you're eliminating all of that. Going beyond the bottleneck. So modern data collection on high volume production lines has to go beyond line level data collection. It really needs to be focused on unit op level. Again, think filler, Gartner, case packer. Able has a concept called fault learning. What fault learning enables us to do is we don't have to go in, and a systems integrator doesn't have to configure every conceivable fault that might occur on a machine. What happens is that we turn fault learning on. And with about 100 hours of production running time, we can usually discern about 90% of the chronic and repetitive faults that are occurring. Fault learning will report out on that. And then those are the faults that the systems integrator will use to configure. However, with fault learning, when that stays on 6 months, 9 months down the road, if what was a one-off fault becomes a repetitive fault, fault learning will pick up on that, and then it can be configured at that point in time. Other things to consider around advanced data collection is making sure that you're not double counting downtime. So again, kind of going back to that view where we had operation 10, 20, 30, and 40, you can't simply just, even like from a Power BI reporting standpoint, you can't just, roll up those assets, okay? Because what's going to end up happening is you're going to double count the downtime. So you have to reconcile it back to a line asset so that you don't do that. But then the Able Logic engine can also feed level 3 through 5 systems. So it can operate at the SCADA level, the MES level, or even directly into ERP if required. Able also doesn't require a data concentrator. So the other common practice that's typically done in data collection is to put in a data concentrator for a production line. We don't need that. We actually prefer when Able is configured to actually talk to each individual machine center and PLC individually. And then commenting on Peer and how you can kind of think about more of a holistic way of data collection for CMMS, think about the full life cycle of an issue. So in a CMMS application, where a work order is created, if a mechanic is at the machine for 10 minutes, 10 minutes is typically what's going to be recorded in the CMMS application. However, with Peer and integration with Peer, we're now able to have a much more comprehensive view, starting with, when was the asset down and an alarm triggered, okay? When was it acknowledged? And then, even after it was acknowledged, if the mechanic isn't at the line, well, maybe it had to get escalated. And then kind of going through the cycle of the repair process, after the mechanic leaves, if there are additional adjustments required by the operators, that's another step in the process. And then finally, the issue gets closed. So with Peer, you have the ability to have this holistic view of an issue, not just what we call wrench time, which is the mechanic time. So to wrap up, Smart Sites accelerators for digital transformation initiatives can provide a 70% reduction in engineering time, a 5x improvement in data fidelity, and then speed to value. So typically when Able is deployed, the customers will see a 4 to 6 week reduction per site in that deployment time period. And then certainly you get advanced functionality along with the other business tools that are in place in the plant and expanding the digital footprint. And with that, we will wrap up. So we can take a few questions on what we covered today. One of the questions that's come in is, can Able be used standalone, or can it be, or does it have to be coupled in with another system? And the answer is both. So Able can be deployed standalone. However, it really works and best suited when coupled in with other business systems. So think of it as a middleware application that has some very relevant analytics that can then be used for an MES project. Or if you have a CMMS application, certainly Able and Peer can provide rich information to feed that process. Another good question is that came in was, are these applications cloud or on-premise? And the applications are cloud natively. However, they can be installed on-premise. So if you're in certain industries that require on-premise software installations, these technologies can certainly be installed on-premise, but natively they're cloud-based and they can be deployed very, very quickly. And with that, I think we are coming up on the hour, so we will wrap up. So thank everyone for attending today. If you have any other questions, reach out to us, and we are happy to follow up and work with you.